Okay, so good evening for Guillaume Baverez. We're going to talk about part 2.
Yes. Part 2 is joint work with Antoine Gigot. And so I will talk about, again, SLE related stuff and also the GFF. And so let's first explain what we actually did. So our results. So our results are mostly concerned with what is called conformal welding. And this is actually, at first, this is a geometric construction, conformal welding. So we were talking a lot about Jordan curves. So suppose if I have a Jordan curve, which can be any Jordan curve, eta, and I'm always going to assume, as before, that it separates 0 from infinity. So I can always find a Riemann mapping that's sending the unit disk to the interior of my curve, and that I'm going to call F. And I can send the outside of the unit disk to the outside of my curve, that I want to call G. Now there is a theorem of Carr-Theodori that tells you that if the image is a Jordan curve, then this conformal map is going to extend injectively and continuously to the boundary. So which means that I can go from the unit circle, send myself to the curve, but then the same happens for G, so I can go back to the unit circle following G. And I have effectively gone from the unit circle back to itself, so I have a homeomorphism of the circle, which I want to call H.
G goes outside as well.
Sorry?
G.
G is defined outside. Okay, so for any Jordan curve, I can define a homeomorphism of the circle like this. And the converse question of if I give you a homeomorphism of the circle and construct a Jordan curve is actually a very difficult question. There is no characterization, but I will not talk about this really. But so if we restrict to a smooth curve, for example, then there is one-to-one correspondence, and if you mod out by the correct gauge, so here rotations of the unit circle, this is giving you a change of coordinates, if you wish, between diffeomorphisms of the circle and Jordan curves. Smooth Jordan curves. And here, what is the gauge? Well, I will need to have unit conformal radius, so viewed from 0, so it means that I have this relation. So that's conformal welding. And I really want to think of it as a change of coordinates between two geometric objects, so diffeomorphisms and Jordan curves. And so it means that on the left picture and on the right picture, I also have I have a change of coordinates, and basically the whole of this, the game of this talk is to understand this change of coordinates, and to understand that there is a Jacobian determinant between these change of coordinates. And so what do I mean by this? I mean that each part of the picture, so the left and the right, it has some symmetry, and the two don't really talk to each other a priori. So on the side of Jordan curves, Antoine spent the last talk telling you that you can deform Jordan curves using conformal maps, local conformal maps. So if I remove a neighborhood of 0 infinity, I can pick a conformal map that is defined there, and it will give me a deformation of my curve by beta. But on the left side of the picture, of course, I have a group. So I can naturally act with some element of the group fixed, and usually I call it phi tilde, which is a diffeomorphism. And I can left or right compose with elements of the group. So what is the symmetry? So I have Jordan curves and for this one. So what are the symmetries? Let me recap. Symmetry would be just left or right composition. And on the right, I have local conformal transformations. And so now you can think of having symmetry. So what if can I have invariant coordinates in this? And in particular, do I have invariant measures? And there is a beautiful thing that SLE 8/3 satisfies a conformal restriction property with central charge equals 0. So you can really think of SLE 8/3, new 8/3, as being an invariant measure with respect to the symmetry. But if you were a physicist, you would write capital D eta as a formal path integral. Now the question is, what's here? So I can always pull back. So I told you that I have a conformal welding map. And so what I do is I have a measure mu here, mu kappa, depending on kappa. And I can always pull back this measure to a measure that I want to call nu tilde kappa. So nu tilde will always be the pullback of the SLE kappa measure. So this guy is sampled from SLE kappa. Okay. And well, naively you would say, okay, nu tilde 8/3 is an invariant measure. But now you're in bad shape because we know that there is no Haar measure on the deduce one. So this cannot be true. Okay, so this cannot be true, but what we want to understand is if there were a Haar measure on diff of S1, could I write this measure as a density with respect to the Haar measure? But so that's the whole question. Can I write at least in inverted commas nu tilde 8/3 as a path integral exponential minus rho nu 8/3 sorry, Haar measure, with respect to Haar measure. So can we write such a statement and can we make sense of such a statement? And that's the whole question. And I would like to call, and if such a rho exists, I would like to call exponential rho the Jacobian of conformal welding. That is telling, so it will be a determinant that tells me it's a determinant of the diffeomorphisms that sends diff of S1 to Jordan curves. And so this statement a priori doesn't make any sense, but I will try to convince you that we can make sense of such a statement rigorously, and that the formula that we can find a formula for this rho. That we can make sense of this formula. This. And we find a formula with rho is equal to something. Rho is equal to 13/12 pi times what is called, well, actually 13/12 times IL of eta. So this is the Loewner energy that I will write down, plus 2 k of eta. And these two functions are very natural functions that come up in the Kähler geometry of the universal Teichner space. So these are very big square words, but I will explain what it means. So this is the Loewner energy, aka the universal UV action. And this is what is called the Welling-Kirillov potential. And I will write down the formula for this potential. So maybe I should say a word that so this universal UV action, it was introduced by Tactajan and Theo. So this is Tactajan Theo. In 2006, I think. And the Loewner energy is something that was introduced by Yilin, and actually also independently by Fritz and Shekhar. But the two definitions were different from the universal reduction, and what Yilin proved is that the two are equal. Up to 1/pi maybe. And the Welling killer potential is also something that was introduced by, or maybe it was studied before by, with less regularity by Nag, Sullivan, and the Soviet school also, so Kirillov and others. And so what are these quantities? So these are things that I can measure from these conformal maps. So IL of beta is 1 over pi integral on disk of f double prime over f prime square. So I'm just writing the formula for completeness, but it's not easy to memorize it. Minus 4 log of g prime of infinity over f prime of 0. And this k of beta is actually this log thing. So k of beta is log of g prime of infinity over f prime of 0. And actually, I think it's also called maybe the logarithmic capacity in some other literature. But these are the point I want to make is that these are very natural functions that appear in this study by Tactero and Theo, and they are potentials on this universal spectrum of space. So they are really natural things to consider. And they also coincide with, so this functional also coincides up to a constant with the determinant of the jump operator across the curve, which is something we already encountered in Antoine's talk, so that we can express in terms of ratios of determinants of Laplacians. Okay, so actually this formula is better written as 26 over 24, because 13 is half the dimension of critical bosonic string theory. And this, I'm not just saying this to justify why German taxpayers are giving us money, but there is actually a connection between this 26 and bosonic string theory that I will try to explain. We're doing in ongoing work with Shin and Belgium. Okay, so maybe I will talk about some briefly about applications of this computation. So the main applications that we have so it gives you, so the first application is one new approach to the quantum zipper of Sheffield. So that was something from Sheffield in 2016, probably. But more precisely, what has been proved by Shin, Nina, and Morris, which is the conformal welding of quantum disks. And I will explain what this is. So this is something that was recently proved by Shin. Hold on. And to explain what this means, I have to go back to the picture. So what this means is that I can decorate this picture by some new type of randomness. So I will consider a field phi that is defined on the unit circle that I want to be considered as the sample from the trace, what we call the trace of the GFF, or the restriction of the GFF on eta. So I pick a GFF, an uncorrelated field on the sphere, and I want to restrict it to the curve. A priori, you cannot do this because the curve is fractal almost surely, but it's actually one aspect that we do with Antoine is that we make sense intrinsically of what it means to restrict the GFF on the curve. Right, so you add this new randomness conditionally on the curve, and what you can look at is the pullback of this field by the conformal map. So what we like to consider is this pullback. But so instead of naively pulling back by just the map, I had this funny Q term where Q is 2 over gamma plus gamma over 2, and gamma is square root of kappa, and I will recall that kappa is between 0 and 4.
Which GFF you take on this here?
So you take the, so actually that's the point, is that we define this measure not by restricting the GFF, but we define it by taking the, so you can define a quadratic form on L2 of the SLE with respect to this natural parameterization. So you have a function space on this, and you can take the Dirichlet energy of the harmonic extension of this thing outside of the curve, and this defines a field, which is really the, but then you have to reweight this field by some power of the zero mode. But I don't want to go into this. But it's the same as the UV field that Shin or Selina are using. Yeah.
So it's what is the GFF up to constant?
It's yeah, I mean it's exponential minus 2qc dc GFF. We have to rewrite by exponential minus 2q. Okay, and then you have this. You can look at this other guy, which would now be. So I have 2 fields. I can form 2 fields on the circle like this, and the statement is that, and I will use this notation phi dot f is equal to this, and the statement is that. So is that if you take if you sample eta from the SLE kappa loop measure and phi from this conditionally on the curve, you sample phi from this GFF restricted to the curve independently, then this pair phi dot f, phi dot g are independent. Traces of the Neumann GFF. Neumann GFFs, which effectively means that they have this covariance property, which is twice the log of 1 over z minus. So I'm lying a little bit precisely because of what Rémi just mentioned, that you have to consider actually infinite measures, including some zero mode, but roughly speaking, the statement is really this, is that if you pick your SLE and on top you have GFF, and then you uniformize back using this funny coordinate change, then you get independent fields that have a very nice distribution because they are just the Neumann GFF. Yes.
So the Q is related to the kappa?
Yes, because I wrote Q equals 2 over gamma plus gamma over 2, and gamma is square root kappa.
Nu kappa is the SLE kappa loop measure.
Yes, yeah. But now I just wanted to make the kappa explicit in the. Okay. So this is something we can prove, and I can say a few words about why this is true and our approach, and by what it was inspired. It was really inspired by what now we understand as the semi-classical limit of this statement actually. And this is a paper by Friedrich and Yevin. And that's basically tell you that you can interpret these. So you want to interpret these things as a path integral precisely, and the path integral will be defined with respect to will have an action. So what is the action for 2 independent Neumann GFFs? This is really the Liouville action in the disk and the complement of the disk. So that would be. So what they prove is that if you look at the Liouville action of this phi dot f plus the Liouville action of the phi dot g, this is equal to the Loewner energy plus this is equal to the Liouville action defining your. So this is the energy defining phi. the UV action. UV action is just Dirichlet energy plus some funny term, but it's essentially Dirichlet energy. And you have Q squared times the Loewner energy. And so that's what they prove, and well, you want to do a path integral with this, so if you take the exponential of this times the uniform measure on the fields, you get the two independent Neumann GFS. On the right, well, this is going to define your P eta, but now what would be the law of the curve? It would be the path integral exponential minus Q squared times the Loewner energy, but this is not what gives you the SLE.
What is S?
It's exactly what I told you. So you pick your function on the curve, you harmonically extend it, and you take the Dirichlet energy of this.
What's the name?
Dirichlet energy. Yeah.
Of the harmonic.
The harmonic extension. Yeah. The Dirichlet energy of the harmonic extension. Okay. Right. And so now the problem is that the problem in the path integral interpretation is that we really want to have that SLE that nu is exponential of Cm over 2 times its well, it's actually exponential of Cm over 2 times the Loewner energy against the eta. Because this is really how you should interpret the integration by parts formula from Anton Stock, is that if I take this seriously, then this measure would satisfy an integration by parts with respect to the deformations over there, and it will precisely be the one I find. So the correct interpretation of SLE is really through this path integral.
So eta is what? The eta?
Yeah, this you can think of it as SLE 8/3, because it's a uniform measure on curves.
So it's SLE 8, so not.
Yeah, so it would be SLE 8/3. So this is of course wrong because the Loewner energy of any curve on the new 8/3 is infinity. This is why it's a path integral. This is why I have inverted commas here. Okay, but now the problem is that I don't have Cm here, I have Q squared. So Cm is different from Q squared. And in fact, in fact it would be 6Q squared, so I might be missing some 6 over here. I think so. Cm is different from 6Q squared. And in fact, they are related by this formula, so you have that Cm is equal to 25 minus 6Q squared. Yes. Which is not equal to 6Q squared. They differ by 25. And the reason is that
Not equal.
yes, yeah. And the reason is that you've been forgetting what we've been forgetting since we were in first year of mathematics, is that we forgot the Jacobian that we were just computing. And you would see that if you plug the Jacobian, you will get the correct thing. Here it's 25 instead of 26 because I'm missing some. This P eta has a partition function, which is the determinant also, and it accounts for one more in this formula. So this is really how we prove so we really this is how we prove it. We prove that this that we give a correct interpretation of this path integral and explain especially why we have this mismatch between the Cm and the 6Q squared. This is how we prove the thing. So this is the first application of this Jacobian, and the second one is some ongoing work that I will just mention maybe orally, or maybe make a little drawing also. So there is a natural generalization. There is a natural generalization of this SLE loop measure to several loops. So we can take 4 loops in the sphere that are conditioned not to intersect themselves and not to be nested, like this. So here I have 4, and there is a theorem that tells me that I can uniformize this to a circle domain. So a circle domain is just a sphere minus Euclidean disk, so it's characterized by centers of the disk and the radii of the disk. And we can compute the, so with Shin and Baldwin, we compute the law of this modulus. So this has a, now when you pull back with this type, this domain has a random modulus. And the modulus is just the family of centers and radii.
Yeah, but at the modulus,
At the modulus, you can fix 3 centers, for example, or you can do. So we compute the law of the random modulus. And the really nice thing is that it actually coincides.
going too fast. How do you sample the curve?
So you do the net. Okay, so you want to use this formula. So SLE is really the back integral with respect to the log determinant of the jump operator. So here, whenever I have 4 curves, any curves in the sphere, I can define a jump operator across the curves. And so it means that you just take n independent SLE loops and you reweight by the correct quantity, so the correct mass of random loops that give you the correct interpretation in terms of path integral. So it's a density with respect to the product measure. You first restrict to the event that they don't intersect, they have this nice topological event. Then you add some exponential of some mass of loops.
With respect to the independent variables.
Yes. It's a density with respect to independent.
Is there a simpler way? Like,
It's no, I couldn't see a simpler way to define it.
I don't know, for loops, well-chosen loops in the CLE or something.
No, because the problem in the CLE is that it's you have to think about it with the Brown loop soup on top, and you have some nasty events of the Brown loop soup that so it's not that straightforward. So even if you take 3 curves, this is not the same model as what Shin, Morris, Bojun, and Giffey have been studying. So they don't have the same 3-point function. Okay. But in any case, we can compute this, and the cool thing about it is that we recover the integration measure from bosonic string theory. And what is this? This is something that had been pioneered by Polyakov in 1981, but the really beautiful paper is by Belamin and Kuzny, where they actually implement this Faddeev-Popov procedure that AJ was talking about yesterday, and it was also. And they rely on this result from Mumford, from 77. And they construct this thing. So first, you have to do this non-rigorous step of using this Faddeev-Popov procedure. But if you accept this step, actually, this is pure algebraic geometry. You can construct this measure canonically using sections of line bundles or whatnot. And the cool thing is that we recover exactly this measure using this probabilistic, using SLE. Actually, there is the fancy thing we should use. Maybe one aspect of this measure, which is also interesting, is that it makes appear some determinants of operators, but not the ones that we really encounter, which is the Laplacian on functions, that we use in statistical mechanics also. Sorry? But it makes appear some determinants acting on vector fields, so which is something slightly different, and that appears quite naturally in our work in the solution theory of the Beltrami equation. I wanted to keep this drawing, but now it's looks like a Jackson Pollock painting. You had a question, Emily?
Yeah, but the same question as Hofer wanted to ask. You said I take the product measure and then I add the mass of the Brownian loop, but okay, so why should we care about this?
There is a simple cascade definition for that.
A simple what?
You can iterate. You first sample a Brownian loop according to the Brownian loop measure, and you choose one of the two connected components.
And then you
You
iterate.
sample one in there, and then you iterate it this way. And you find, and as soon as you get n loops, you have your measure. That's a different construction, but it gives the same measure at the end.
Okay, so are there any more questions, by the way, or? Okay, so in the remaining part of the talk, I think I will give some hints of how we prove this. Well, first make sense of this Jacobian, and then how we compute it. And maybe I will, if I have time, I will explain how we prove the coupling with the GFL. But so Antoine had this nice toy model with the Gaussian, and we also have a finite dimensional. We also have a finite dimensional toy model for this Jacobian computation. So how do we work? So the toy model is the following. So you pick M1 and M2 to be two manifolds. So secretly, I really want to think of this as being diff of S1 and M2 of being vectors, but I want to focus on the finite dimensional case for now, and I'm going to assume that they have dimension n, finite. And you want to have a volume form on the, but okay, you can think of, for the purpose of this talk, you can think of being both Rn. And I want to pick two volume forms on them, on these. And what I want also is a family of vector fields that preserve these volume forms. But so the example here is just dx1 wedge dxn. So just the Lebesgue measure on Rn. And what I want also is a family of invariant vector fields that are independent. So if you wish a tangent frame on M2 that preserve mu2, i.e. the Lie derivative of mu2 with respect to yj is equal to 0, and that would be the Lie derivative. But if you are unhappy with this notation, you can just think of y1, yn to be dx1, dxn. And I want to also to have vector fields x1, xn, which are the same on M1. And now I pick psi to be a diffeomorphism from M1 to M2. Okay. And well, I can always say that I can always pull back mu2 to M1 and I get a measure. And I can always write that this has a density with respect to mu1 that I want to call exponential minus rho for some rho. And this exponential minus rho is what I understand as the Jacobian of my psi measured in these invariant coordinates x1 and xj. And so how do we compute this? So the thing is, when I want to go to infinite dimensions, these new ones and new twos, most of the time they will not make sense. So I need to have a way of computing this rho without having these measures appear, but just using my vector field. So these vector fields, secretly, I want to think of x1 being generators of left and right composition on the s1, and these yj as being the generators of the phi. But here we're still in finite dimensions. Okay, so now if I pick a smooth function on with compact supports on the M1, I want to establish an integration by parts with respect to the measure psi star nu2. So I just have the integral of Lxj f psi star nu2. Well, on the one hand, I can use the Leibniz rule to say that this is the integral of Lxj f against my favorite measure psi star nu2 plus the integral of f Lxj of psi star nu2, but since I write it this way, this is just actually a minus Lxj rho, and so I get Lxj rho times exponential minus nu1, which is just the measure I started with. So I have an integration by parts like this, but I still need to tell you what this is, and I claim that this is 0. And why? This is because of Cartan's formula. Cartan's formula tells you that the Lie derivative is the commutator of the Dom differential and the contraction with xj, which means that this is really okay, and now I claim that both are 0. So this is the differential. This is so now this gives me an exact form by definition. So it's equal to 0 by Stokes. So this is by Stokes, and this is the differential. This is the differential of the top form, which vanishes. So it vanishes as a differential of the first form. So this is equal to 0, and I have my integration by parts here, which tell me that when I integrate the Lie derivative of f against my unknown measure, I just get the integral of f times the Lie derivative of the unknown function. But now what I can do is to use a change of coordinates. So I can also say that this quantity star is also equal to the integral over m2 of the Lie derivative along the push forward of xj of the same thing. But now against nu2, because when I push forward to pull back, I get the same measure. And so, okay, so now I use again the Leibniz rule, which tells me that this is the Lie derivative along this vector field of f. It's plus the Lie derivative of my measure. But I can write the Lie derivative of my measure as just the divergence of vector field with respect to this measure. So this is really the divergence of the vector field psi star nu2 against with respect to the measure nu2. I integrate with respect to nu2. And now I need to compute this divergence. So now I can expand psi star xj on the basis of yj's. I can always do this. And now this guy is just equal to, so this is equal to the sum from 1 to n of the divergence. So these are some functions beta of n2.
You mean they are not about star xj?
So, sorry? Yes. But this is just the sum of the divergence with respect to nu2 of this beta jk yk. But now I know that the yk preserves nu, so I just get the sum from 1 to n of the derivative of with respect to yk of beta jk. So when I put everything together, I get that the differential of rho, so the derivative of rho along some vector field, is equal to the sum of Lyk beta jk. Maybe I want to call it back to my initial manifold. And now the measure does not appear. But of course, they are hidden. These measures are hidden in these coefficients because the vectors that preserve the measure, so they know about the measure, and these coefficients also know about the measure somehow. But this formula does not involve any integration against some unknown measure. And if I have such objects, well, then maybe I can hope that in infinite dimension, I can still make sense of this sum and obtain a convergent sum and be able to compute it. So, in other words, this gives me, so the integration by parts that I just showed you gives access to the differential of rho. To d rho. And then, so I can hope to first compute d rho and then integrate it to something. So this is actually what we do. We never compute this Jacobian of the welding. We compute this differential, and we see that it coincides with the differential of these potentials that we exhibit, that I told you about. So that was for the toy model. And I think in the last 15 minutes I will say a few words about how we implement this method in infinite dimension. So it all starts with some operators. As always, can I erase this because it's actually oh, okay. So on the right-hand side of the picture, we already have some operators that Antoine introduced. So now I need to understand what are the operators that generate the symmetry on the left-hand side. So as I told you, I need to generate motion by small, by composition by small diffeomorphisms. And I will do this on the right, because if I was doing it on the left, I would need to use the letter L. And this has already been used in the previous talk. So I'll do right composition instead. So now what we're going to pick a family of diffeomorphisms that are going to be analytic actually. And I want to generate them by some Bertrami differential mu, so we'll explain what it means. By mu, so this means that d bar of, well actually no, then well, generated by some vector field. Let's write, okay, I can write an expansion like this. So if I pick a z on the unit circle, can be able to write some expansion like this. Plus t bar where this W is holomorphic in D, and this W tilde is holomorphic in D star. And they have to be related in some way, because I want the sum of these two guys to preserve the unit circle. So they are related in some way. But let's take this for given. Okay, and now for all test functions, so you can define some test functions in the way as Antoine did it in the previous talk, by having a dense, nice subspace of functions on the space of diffeomorphisms. F. I can define some operators through this first order expansion. And now I'm going to call it R. Okay, so I want to call it R mu because there is a Beltrami differential mu. So okay, let's do RW then. RW of F plus, sorry, it's T plus T bar plus a little of T. And this is defining operators. They are densely defined on this mu tilde. So defines operators are W, RW bar. So they are unbounded, but you get some operators on L2 mu. And so I've been talking about SED 8/3 from the start, but you can pick any kappa, it works. You would just have to add some work. Okay. So I have some operators like this, but now the key thing is that these guys are generating the motion by some diffeomorphism of the unit circle, but I have no idea. So I have a new diffeomorphism here, and I can look at the curve that it welds. So I would get an eta t here, and it's not clear how the two are related a priori. It turns out that if you look into a book of about quasi-conformal maps, you can solve infinitesimally and find the vector field that will generate the motion of the curve. The question is, so this is basically if you look up in the book of Alforce or other people, you can compute the corresponding variation phi t of eta, well, eta t. Eta t, which welds the homeomorphism H composed with phi t tilde minus 1. And so in fact, you can always say that. So you have a curve eta t now that corresponds to this guy, and this eta t I want to write it as some phi t of eta, and this phi t will be conformal everywhere except for a small neighborhood of 0. So it will have a Laurent expansion. It will have a power series expansion in the neighborhood of infinity. And so you get that phi t of z is z plus some from maybe 1 to minus infinity to minus 1, say, of some beta n mu times z to the n plus 1. And these beta, well, they are the same as the betas I introduced before, basically. So they are the Laurent expansion of your map, and they're explicit. I can even write a formula for you if you want, but it's not really important. Beta and mu is something like 1 over pi. Yes, integral. So now I'm going to regret not using Beltrami differential, but So f prime of beta square over f of beta to the n plus 2 mu of zeta. Zeta. So actually, I can write it as a contour integral, possibly. This is so of w. What is my convention? This is so of w tilde of zeta. Zeta. So you have a formula for these guys. And now the next step is to compute the divergence. So here I needed to compute. I need to compute the variations of this beta. So beta jk, the j really stands for the mu here. And now we need to compute the variation of all these guys and sum it up all the way to infinity. So what is the variation of these guys? It's the variation now when I move the curve by some vector field, which is actually the vector field zn plus 1. So I need to compute, so this is step 1. The step 2 is I need to understand the variation of these betas with respect to this local conformal transformation. So I need to compute ln of beta n. Step 2 is compute ln of beta n w. So now I should really call this w. So I need to compute this guy, and step 2. So this is doable again by some formulas. So this is the operator from OpenStock. So this again is giving the formulas of alpha, some quasi-conformal maps are useful, for example. And step 3 is you have to sum it up. So you have to compute the sum. Compute the sum from minus infinity to minus 1 of Ln beta n. And by some kind of magic computation, it actually sums up. So it's easier to sum up all the way to 1. And then you get that it is 13 over 6 times the Schwarzian of f evaluated against your vector field. So the Schwarzian derivative. So I will write this in four letters. 12 I pi integral of SF of zeta, W of zeta, d zeta. And this by Cartesian and Theo. This is equal to the, 13, maybe over 6, or now maybe a bit less, but times the differential of the UV action evaluated on your vector field W. And so I was needed only to sum to 1, but actually the terms of 0 and minus 1 are explicit, so you can just add them to the sum. And when you add them to the sum, you get exactly the Welling-Kirchhoff potential that I mentioned earlier. So in the end, yeah, you are able to sum this really nasty sum, get a multiple of the Schwarzian that coincides exactly with this 13. And so it tells you that, so from the previous step, from the finite dimensional step, that the correct interpretation of the rho is that its differential is really the same as the 13 times the differential of the universal UV action. So it gives you the interpretation of this rho as being this 13 times the UV action. And okay, so I just have a few minutes, so maybe now I can say a few words about the next step. So the next step is that, here we were looking at simply connected surfaces, but this method is actually completely intrinsic, so it does not care at all about the fact that you work on simply connected domain. So if you are on a multiply connected domain or a compact surface, in fact you are just adding a finite dimensional problem on top of the infinite dimensional one. So really the core thing is to understand the infinite dimensional problem, and then you have a bit more geometry when you have non-simply connected things. But the method really passes to more complicated topologies quite easily, relatively easily. At least you don't need new ideas somehow. So yeah, I guess I will stop here and well, yeah, thanks again for listening.